We present a new image-based method called light field transfer for compositing real and synthetic objects in the same scene with near-field lighting. By using a light field interface, which requires only 4D datasets, we provide multiple bounces of global illumination without the need for a model of the rendering properties of real objects. We can support dynamic scenes because our method can be performed in near real time. We now describe in detail the process of rendering images using our light field transfer method. First, direct lighting in the real scene illuminates real objects. A light field of the real objects lit with direct illumination is captured by the light field interface. The renderer lights synthetic objects with direct lighting that is calibrated to the real scene. It then generates a light field to be sent onto the light field interface for projection. Now the real scene is illuminated both by direct lighting and by the light field interface, which contributes near-field illumination from the synthetic scene. Similarly, the synthetic scene is illuminated by direct lighting and also by the captured light field, which contributes near-field lighting from the real scene. We can iterate this process for multiple bounces of global illumination, and then create the final result by capturing and rendering the relit scenes and compositing. In our experimental setup, we use a lens array to multiplex 4D light fields into 2D images that are captured and projected. Because our algorithm iteratively transfers indirect lighting, we can pause computation and infer the contribution of individual bounces. Here we decompose a scene with a synthetic green block and a real red block into direct, second, and third bounce contributions from both objects, and show that the sum of all contributions provides similar results to a purely synthetic scene rendered with path tracing. We now introduce a scene that demonstrates specular reflections shared between real and synthetic objects. The scene consists of a synthetic hand holding a photo frame above a wooden table and a real shiny bowl and bust placed on a checkered surface. A glossy reflection of the synthetic photo is visible on the bottom of the shiny bowl, and as the photograph rotates towards the viewer, a reflection of the bust becomes visible. A real hand inserts an orange next to the bust, and its reflection can be seen on the photograph. The photograph texture is temporarily turned off while we gradually change the material from glossy to matte. Our method, for the first time, enables multiple bounce global illumination between dynamic, real, and synthetic scenes. Finally, we see that as the frame moves away from the bowl, more becomes visible in its reflection. As it approaches again, we can see more detail, until we start to recognize the structure of the eyes and mouth of the face. Our last example shows soft shadows and diffuse-diffuse interactions for a scene consisting of a synthetic sun and planet and a real mannequin face. Both the planet and the face are illuminated only by the synthetic sun. The planet obscures the sun's illumination of the face, casting a soft shadow that becomes more defined as it approaches. Diffusely reflected light from the face illuminates the backside of the planet. We briefly observe the planet illuminated only by the light reflected from the face. The shadow falls on the contours of the face, pronouncing its structure and spatial relationship to the planet. In conclusion, using light field transfer, we have presented the first videos of global illumination in time-varying hybrid scenes. We presented example scenes with multiple bounces of indirect illumination, glossy reflections, soft shadows, and diffuse-diffuse interactions.